I'm Manan Shah, and I'll be discussing my work on disease propagation in social networks. So a quick overview of how the talk's going to go. We're going to have a few key subsections. The first regarding what the problem definition and specific challenges are, then an overview of the solution in two key components, then a few experiments and discussion. So first, what are we actually trying to do? So the goal of this work is to be able to define a disease distribution based on social media data, for example, in particular from Twitter. And so we have a ground truth already, which is the CDC ILI distribution. And as many of you guys already know, this is very similar to the Google Flu Trends work regarding using keywords from Google search terms to make predictions about the ILI distribution. And so our goal is to utilize Twitter data to perform similar end goal. But there are a few challenges to our work, and there are three particular challenges of note. The first challenge is adequate elimination of irrelevant tweets. So Twitter is full of spam and full of irrelevant information. And it's very important for us to be able to distinguish between tweets regarding sick music, for example, and sick individuals. And so this is one of the first most important challenges that Google Flu Trends and prior works have yet to address. A second important challenge is regulating media hype of diseases. So for example, diseases like Ebola and the recent Zika virus, although they are very important and are indeed infectious, do have issues regarding news hype of those diseases as opposed to the more common and more widely spread influenza disease in the United States. And finally, we'd like to generate a model that can update with respect to time regarding recent keywords from Twitter, recent hashtags, et cetera, all of which requires a model that's fast and efficient. And so current approaches do exist, but they are few and far between. And most approaches follow a similar strategy of two key steps. The first is identifying keywords that are relevant for Twitter. So for example, sick, flu, or influenza, and formulating SQL queries that identify which tweets match these certain types of keywords. So for example, in this particular instance, a user might search for tweets that contain the word sick and contain the words flu, but does not contain the word medicine. Does not contain the word music. And then generate a list of all the tweets that match these criteria. And these lists are generally often between 20 and 30 distinct words long and aren't generated by any specific type of means. They're commonly used. The second step is a regression step. And what this means is that the tweet counts that are obtained from the first step are applied to some sort of either linear or multivariate regression model to make a prediction that matches the ILI distribution. And our improvements to these particular types of models are as follows. We first define a new method for obtaining a list of hashtags or keywords that best represent diseases. So instead of using a subjective list of random hashtags that may or may not represent a particular disease, we instead define a method to best encompass a holistic sample of tweets that are most relevant to disease. We second define a classification procedure that distinguishes tweets into three different categories: self-reporting, non-self-reporting, and spam tweets, which we use to further classify our subset of tweets to more adequately represent our tweets as either disease-related or non-disease-related. And finally, we forego the entire step of the regression model and simply use our tweet frequency-based analysis as a result for prediction, performing even better than Google Flu Trends and the latest published papers on the subject. So a highlight of our results include a correlation, a Pearson's R value of 0.983, representing the best yet to date with these networks. We additionally demonstrated a robustness of our approach to external noise, and we demonstrate an application of our networks to international disease simulations. So let's get started on the actual pipeline itself. So this is a simplified version of what the pipeline will look like. We start by generating or identifying key keywords that are relevant for making a prediction regarding disease. We then cluster tweets based on TF-IDF vector similarity, generate feature vectors for tweets, and classify relevant tweets by self-reporting, non-self-reporting, or spam, which I'll discuss more in the future. We then generate a distribution based on these tweets and evaluate how well this distribution conforms to the ILI distribution. And so our pipeline can be loosely broken down into two key subsections: keyword identification and the subsequent cluster elimination. And so keyword identification can further be broken down to three key substeps, of which first we define an initial keyword list. We then expand that keyword list by treating the first list as a seed and generating further keywords that might be similar to the seed list. And then we model each hashtag as a corpus and generate TF-IDF vectors for each tweet in the hashtag or keyword corpus. We then perform cluster elimination, whereby we cluster tweets based on TF-IDF similarity and isolate salient tweets within each cluster, eliminating or keeping entire clusters as needed. We finally generate a resulting analogous ILI distribution. So first on keyword identification. A quick overview of how the process might look like is as follows. In particular, the first step is initial keyword identification. And what we do here is we first start with a list of about approximately 700 keywords that are relevant for analysis or are mentioned on Twitter that are all infectious diseases. So you start with a large list. And the problem with such a large list is that a lot of these tweets are either irrelevant, outdated, or simply repetitions of prior tweets or retweets that aren't actually significant for the ILI distribution. So we like to define a metric to sort these keywords and identify the best keywords that can distinguish between the keywords that are less salient and the keywords that are most important. And in so doing, you can see a little bit more about how this metric works in the paper. We define a P, or a popularity metric, that best represents, that weights both the number of users that tweet a particular keyword over a span of time, as well as the lexical similarity between different tweets. And using this metric, we sort our keywords and identify the top 63 tweets, top 63 keywords that best represent heterogeneity and recency in tweet data. So with these 63 keywords identified, we'd like to expand our list. And the way we do this is we define our initial list of 63 keywords as a seed list. And we identify the top k-grams between each pair of keywords within the seed list and add those to our initial list. So a concrete example might be if our seed list contains keywords influenza and dengue, and a common symptom for both influenza and dengue is headache or runny nose, for example, different types of n-grams. We would include those n-grams in our keyword list to make sure that we include tweets that individuals might pose that do not directly indicate their individual sickness, but do indicate symptoms that are relevant for that particular sickness. And so we then narrow down our initial database of 100 million tweets to 400,000 based on our expanded keyword list. So the second step is, what do we have to do with those 400,000 tweets? So once our initial elimination of tweets and filtering yields 400,000 tweets, we'd like to cluster these tweets by TF-IDF metrics for a reason I'll explain in a little bit. So once we cluster these tweets, it's necessary to be able to classify each cluster as either relevant or irrelevant. And what I mean by this is, once we have a list of tweets, there are tweet differences between tweets that are either I'm feeling sick, or this music is sick, or different types of tweets within these type categories that must be differentiated for an accurate representation of the ILI distribution. So we define 3 distinct categories. The first is tweets that are disease-related, within which we have subcategories of people self-identifying tweets and non-self-reported tweets. And the second category is non-disease-related tweets, which are simply spam. So let's go into these categories in a little bit more detail. The first category is self-reported tweets within the disease-related category. Self-reported tweets are those that are those tweets that represent an individual giving his or her public condition, representing his or her condition. So for example, here you can see a tweet regarding, I've never been more sick in my life than I am right now, et cetera, et cetera. And this is where an individual clearly says that he or she is sick and is therefore certainly important for our analysis of the ILI distribution. And we keep those tweets. Non-self-reporting tweets are tweets that, although they do represent information about the flu or about a certain illness, are not with a certain individual talking about that illness or a self-reporting of that illness. Therefore, we exclude these types of tweets from our analysis, and an example can be shown to the right or left. And finally, there are tweets that are simply just not disease-related. So for example, tweets that consist of, for example, this tweet that is a tongue twister, including the word sick, that has nothing to do with sickness at all, and does not have anything to do with individual self-reporting sickness or an external report of sickness. And we also exclude these tweets from our analysis. So once we have defined 3 different categories for tweets, we then perform categorical classification using a simple random forest classifier differentiating between these 3 types of categories. Our classifier performs quite well in 10-forward cross-validation, and we manually label a set of 300 tweets so we can train and predict with this given classifier. So once we have such a classifier, we can then eliminate different clusters based on a certain threshold t. So we classify n random samples within each cluster that hopefully are representative of the overall cluster. And given if more than t tweets weighted by medical relevance and weighted by other types of factors, along with the initial prediction given by the random forest classifier, are deemed to be irrelevant, we would discard the entire cluster. This is primarily for reasons of efficiency, because as we scale to more than hundreds of thousands of tweets in our final list, we'd like to make sure that our algorithm can be both efficient and can make these predictions in rapid real time. So our output is a real-time disease distribution that matches the ILI curve. So now let's talk about how we evaluated our model. Our model was evaluated based on the Stanford Spinner dataset, which is a dataset of over 100 million tweets, which we then stemmed to 400,000 and subsequent stemming via the cluster elimination procedure. We compared the distributions of 4 distinct methods: the CDC ILI distribution, the Twitter distribution that we proposed, that is generated from our proposed method, an SEI or mathematical model, which essentially models the spread of a viral disease, for example, parameters from influenza A, over time, defining individuals in 4 distinct categories: suspected, exposed, infected, and recovered, and then propagating based on certain conditions that are modeled based on the real-life spread of influenza. And finally, a distribution of what common methods would use. For example, the queries that I defined previously with SQL-like finding and eliminating very basic cluster information without any subsequent classification. And the primary results for our algorithm can be shown in this graph. In particular, note that the thick black line represents the CDC ILI distribution. The dashed green line represents the baseline method. The dashed blue line represents the SEIR simulation method. And the thick red line represents our approach. There are a few points to note within this graph. The first of which is that the blue line vastly overshoots at the beginning around week 50 to week 55 and undershoots at the very end, indicating that for certain reasons, including the recurrence of diseases and different types of transfer, the mathematical model is not as efficient as it could be at predicting the spread of disease over time. In contrast, the previous methods do the exact opposite with Twitter analysis. They undershoot at the beginning and overshoot at the very end, and miss important anomalies in the middle around week 60 to week 65, where there are slight bumps in the ILI distribution that are important to note, specifically when you're targeting disease curation methods in particular areas, but are not caught by the green line. In contrast, our method's proposed red line both includes these types of anomalies and best matches the ILI distribution with the correlation coefficient outclassing those of prior methods. So future work in our particular area involves 3 specific areas of improvement. The first involving spatial disease location, the second involving cascade prediction, and the third involving international modeling. We have tried preliminary simulations in defining graphs across the United States and across international regions of how disease spreads over time, which can be seen in the paper as well. But in particular, we'd like to also predict the spread of disease over time and how long diseases might take for their entire extent. And we'll also like to predict where diseases are located and where these spikes are occurring, which is all readily available with Twitter geolocation data. I'd like to acknowledge the following individuals for their contributions to my work, in particular my mentor, Dr. Oksosik, for really helping out regarding specific types of implementation strategies. And this code is open source and available at the URL below. So thank you.